our learning intentions. We will be learning to synthesize logic circuits today, and our success criteria. You will be successful if you're able to solve at least one question on your own. Let us begin by recollecting what we learned in the previous class about logic gates. There are three basic gates: AND, OR, NOT. The AND gate will have an output condition if both the input are true. By true, we are referring to the 1, and by false, we are referring to the 0. So if there is an input, we'd say that the input is true, and the true condition is marked by a 1 in the trace table. And for the OR gate, to have an output condition, any one of the input conditions has to be true. For the NOT gate, whatever input we provide, it will be inverted as the output. If the input is true, the output becomes false. And then there are three derived gates: the NAND, NOR, and XOR. The NAND gate is a combination of the NOT gate and AND gate. The NOR gate is a combination of NOT gate and OR gate. And XOR is an exclusively OR gate. I hope by now you have a notebook with you so that we may try to design a logic circuit and thereby see how logic gates could be put into practical purpose. Now, let's look at this statement. An alarm Y sends a signal Y equal 1 when certain fault conditions in a chemical process are detected. Now, an alarm Y, it refers to a specific signal that is generated in a condition. So this is the output, and the input is the certain fault conditions, and we will look at that in this next table that follows. The inputs are A, T, and S. It's under the input column, and the binary values are, they take values of ones and zeros, and the condition is given in the third column. Now, A is acidity. So acidity, if it is greater than 5, you get A equal 1. If acidity is less than or equal to 5, you get A equals 0. The next condition is for T. T is the temperature. Temperature, if it is greater than or equal to 120 degrees Celsius, you get T equal 1. And if the temperature is less than 120 degrees Celsius, you get T equals 0. And the third input is S, the stirrer bar. If the stirrer bar is on, you get an S equal 1, and if the stirrer bar is off, you get an S equals 0. So these are the 6 different inputs of 3 conditions. Okay. Now let's look at the third part of the question. This is a logic statement. The alarm Y returns a value of 1 if either temperature is greater than or equal to 120 degrees Celsius and stirrer bar is off, or acidity is greater than 5 and temperature less than 120 degrees Celsius. So this statement and this table might look confusing in the beginning because we have not yet broken it down. These are just raw facts and abstract data which we have to make it into meaningful information for us to proceed in making a logic circuit. Don't worry about that. Just go through this question for now, and let's discuss how to break it down in the next step. Alright, so since we have this information, we'll go forward. The step 1 will be to rewrite the given statement using the table of inputs given. This is the table we saw in the part 2 of the question, and in part 3 we have seen a statement, so we'll just write it in different steps. The first step is the alarm Y returns a value of 1. So this was also very evident from the first part of the question, which says that y is equal to 1. Now the second part is temperature is greater than or equal to 120 degrees Celsius and stirrer bar is off. Now by looking at the table, will be very easy to find out that if temperature is greater than or equal to 120 degrees Celsius, T is equal to 1 and stirrer bar is off is S equals 0. So T equal 1, we're using the same and make it S equals 0. And the next part of the statement is acidity is greater than 5 and temperature is less than 120 degrees Celsius. Now let's look at acidity is greater than 5, which refers to A equal 1 and temperature less than 120. Temperature less than 120 refers to T equal 0. So the statement can be rewritten as A equal 1 and T equals 0. So we can see that y is equal 1 if T equal 1 and S equals 0. And also another part of the statement is A equal 1 and T equals 0. There is an OR in between. We'll discuss it next. In step number 2, we'll decide which logic gates we are going to be using in this statement. Now, we're just writing the statement completely. Y equal 1 if T equal 1 and S equal 0, or A equal 1 and T equals 0. Now from this statement, it is very evident that there are two and one or in the statement. We'll go to the next step now. In step 3, we're going to take the truth table and assume the requirement and try to fill it up according to the condition given by the question. Now we know that y is equal to 1 if T is 1, S is 0, and y equals 1 if A is 1 and T is 0. So that's the same thing which we are going to draw here. We just fill up the y column specifically, like y is 1 if T is 1, S is 0. The same thing will come down also. If the T is 1 and S is 0, we have y equal to 1 here. And if A is 1, T is 0, we get a 1. If here also A is 1, T is 0, we get a 1. You should know that this question is not about filling the truth table alone, but we have to design the logic circuit. So the logic circuit should satisfy these conditions. Now let's try and figure it out. Let's go to step number. In step number 4, we will be recollecting these truth tables from the previous lesson. So we'll be having the and or, as we know that there are two and one or in this statement. And just to be safe, we'll be learning the not as well. As we know that NOT gate might be useful to convert a 0 into a 1 and a 1 into 0 as and when necessary. So let's look at the AND gate. If you remember our beginning of the lesson today, we kind of recollected the AND gate statement to be the output is condition is true if both of the inputs have to be true. Okay, so both input to be true means both inputs to be ones. Okay, and let's look at this A and B as input and Z as the output. Now for both the input conditions to be true, it's possible only in the last case. The other case is A and B, both conditions are false. In the second one, A is false, B is true. Third, A is true, B is false. The last one is having both of these statements to be true conditions, and only in that case we get an output. So that's the AND truth table. Now let's look at the OR truth table. Difference is that here any one of the input is enough to be true in case of an output from the OR gate. Okay, so here in the first statement both are false, so there is no output or false output. So and when there is one input to be in the true statement, we get a true output, and that is the same for the third one also. If one is true, we get a true output, and the last one, both are true, we still get an output. And NOT, as we discussed before, is a single input, single output gate. If you give a 0, you get a 1. If you give a 1, you get a 0. In step number 5, we'll be just trying to synthesize the logic circuit using the different gates as segments. This refers to just drawing it as a trial and error using the different gates that we know from the statement. The statement says that y equal 1 if t equal 1 and s equals 0. That's the first statement. The second is a equal 1 and t equals 0. That's the second statement. And there is an OR in between. So these statements try to give the hint that there is an AND gate between t, s. There is another AND gate between T and A, and an OR gate in between these two gates. So we'll just draw it here and see, without connecting anything, we'll just place it. Okay, so first we have A and T here. We'll just place the AND gate there, and then we're going to keep the OR gate, and then we'll try another AND gate between the T and S. Okay, now these three are there. Let's look at these numbers again. Now T is 1 and S equals 0. There is a T is 1 and S equals 0, which means that some or the other number has to be changed. Okay, so for that, for changing the value from 1 to 0 or 0 to 1, we can use a NOT gate. So we'll hold that there, and then here also we see a equal 1, t equals 0. So here also we need to use a NOT gate. The question is whether we should keep it from the t or the s, from the a or the t. So for finding out that, we have to go with the trial and error. So we'll just keep it as in between the s and in between the t for these statements. Now let's just connect the diagram so that we get the proper circuit. So the A is connected to the AND, and then T is connected and downwards as well, and this is coming to the AND gate, and the AND gate outputs are connected to the OR gate, and the OR gate is giving the output Y. Alright, now we have a trial circuit. We have to just see whether this works with the help of different inputs. Let's take a look at how to try to solve this by the different inputs and get the specific output. In the first case, we have A, T and S to be zeros. So we'll try these three inputs: A 0, T 0 and S 0. We'll just trace it and how the input changes towards the output side, and then we'll just fill it up in the truth table. Alright, now let's look at the first 0 from A. It's coming through this line towards the AND gate, and this 0 T is coming here and goes through this NOT gate to the AND gate. Alright, when the 0 comes through the NOT gate, we know that it will be changed. Alright, before we write, we'll just make one more point here, that the 0 is coming here and going up and going down. So only the 0 going through this line gets changed. The other one remains as a 0 itself. Alright, and S0 goes through a NOT gate and comes out as a 1. Alright, we'll just see how the values are. So that is the 0, this is the 1, here's 0 and the 1. I hope you could understand why we got this one here 1 and this one is 0 itself. Is this the same line? Without any change, it goes down here. It goes to a NOT gate. Alright? And outside of this AND gate, if you remember the truth table, for 0 and 1, that is only one input condition is true, what do you think should be the output condition here? And that's the same here as well, because only one input condition is there. Since the AND gate requires both the input conditions to be true, here there will be no output, or no output is symbolized as a 0. And here as it's the same thing, 0. And if both are zeros going into the OR gate, right? So the OR gate can work the output if any one input is there. But in this case, there are no inputs, and because of that, there will be no output. And we just mark it in the truth table as A0, T0, S0, and Y0. Step number 6 continues with the next set of inputs. We'll try to do it a little bit faster this time. Now A0, T is 1, again 0, and S is 1. Okay, and how these values change over the different gates is what we'll be tracing. And the 0 travels through this line, so there's no change with that 0, but the 0 comes from the T is changed by the NOT gate, and this 0 goes down as well, same. The 1 from the S comes to the NOT gate and becomes a 0. Okay, and 0 1 going into AND gate, there is no output. 0 0 going into output gate is also having no output. When both zeros are going into OR gate, again no output. So Y is 0 here. Now the third set of input is A0, T1, and S0. We just look at how it changes. Now this one, A will be the same here in this AND. The T will be changed here. The T will be same for this AND gate, and S will be changed through this NOT gate to the AND. So that is the value of the 0 and 0, and here's 1 and this one 1. Now we know that when both inputs are true, there will be an output from the AND gate, and that happens here. The other one has no output, and from one true condition as input for OR gate will give an output, and that's what we'll record in the trace table. And the next is 0 1 1. In that case, we can see that there is no AND gate with both of the true input conditions, which makes the output of AND gates as 0, and thereby the output of Y also remains 0. Let's look at the next input condition, 1 0 0, and 1 0 from A and T will get converted to 1 1, and the 0 0 from T and S go into 0 1. We know that here we have two true conditions of input in this AND gate, and that should give a true output. And here there is only one input, so it will be a 0. And from 1 and 0 going into an OR gate will give a true condition, or 1 as output. So Y is equal to 1 in this statement. Now next is 1 0 1, and this 1 0 from A and T becomes a 1 1, and that definitely will give an output because it's an OR gate, and if we get a 1 here, that is enough for the output. So there we have Y equal to 1 for this condition as well. We'll fill in the table and go ahead. Next is 1 1 0. Now here is a tricky part. The 1 1 will be a 1 0 here, and this 1 0 will become a 1 1 here, and this 1 1 in an AND gate gives a 1, but the other one there's no, and since there's 1 here, you get an output and the table is filled. Again 1 1 1, Here will be 1 0 and a 1 0. Since the 1 0 going into an AND gate will not give an output, the Y output is not there. Alright, so we have been able to fill up the truth table according to the condition given in the statement. So this circuit is correct. If there was any difficulty in filling the truth table accordingly, we should be using the NOT gate in the other place. That is, when in between T and S, we should use it in T, and in between A and T, we should be using an A. In case, only in the case when there is a mistake in the truth table. Alright, since everything is right, we are moving forward with this. And the truth table is finalized. We fill it up. So we have seen that when T is 1 and S is 0, we get Y equal 1. And that's the same in here as well. T equals 1, S equals 0, Y equal 1. And when A is 1 and T is 0, we have Y equal 1. When A is 1, T is 0, we have Y equal to 1. So these are the 4 specific outputs given in this question. We have reached the end of today's lesson, and to conclude it, we'll just rewind and see what all the steps we have followed. First, we had the question and we broke it down into simple terms, and we made it into logic circuit statements. That is the logic statements, like for example A equal to 1 and T equal to 0, or T equal to 1 and S equal to 0. Those kind of statements are easy to understand in terms of the logic circuits. Okay, and then we try to use the different gates and OR, and we try to experiment with the NOT gate to find whether it suits in or not. So the trial and error was to check with the different inputs to find whether the output specified could be obtained. And we tried with all the inputs A, T and S with the different zeros and ones combinations, and then it is a little bit complex topic. If you feel that you have not understood the concept, or if you feel less confident in solving the questions, do not worry. With practice, you will be able to get there. Thank you, and see you in the next class.